Boston, across the pond, but actually have a large office here in Cambridge as well. Joss has been at MathWorks for almost 20 years, but before that did a PhD in laser physics at Oxford and did a short stint as a postdoc there as well. He's promised to sort of wake us up and entertain us this afternoon with a story on how to use MATLAB and Docker to do deep learning. Joss, over to you.
Thank you, Mark. So yes, Mark's pointed out that I'm in the doldrums. There's a large group of you to the top right. I don't know why the group is closer towards me. You like to be far away. You're making my life difficult. Thank you very much. I'm going to pick on the ones at the back. I'm a senior engineering manager at MathWorks, so I normally do development. That's what I spend most of my time doing. But actually, at the beginning of this year, I got to spend a couple of weeks playing around with our deep learning tools, mostly with the aim of putting together a talk that I gave at GTC in San Jose. I want to take you through a story of me doing deep learning. The reason I did it was actually because I developed this Docker container that's up on the NGC cloud, but that was somewhat peripheral to this whole story. So, as with all stories, I need a couple of motivating factors. I need to have to do something. So these are the things that I want to do. Can you guys at the back see it? You can. Oh, good eyesight. Awesome. Thank you. Those of you who can't, come forward. So I want to do two things. I'm going to take this story in two halves. The first half is building a scalable web application to do genre recognition of music. This seemed to me like something that I could do. I could probably approach this problem. It was interesting to me personally, and so I'll take you through most of the time how I did that. The other one is a little bit more of a traditional deep learning example. Here we're going to try and segment and semantically segment brain tumors and work out which parts of brains are good and which parts are bad. This has got some very interesting problems when you come to the compute power, but the common theme between both of these examples is going to be how much time it's going to take to do certain things. So almost every deep learning workflow looks like this. It goes, I need to get some data. I need to access it. I almost certainly need to do some sort of pre-processing on it, and we'll do a little bit of pre-processing in both cases. I'm then probably going to have to try and select some sort of network to train on my data. I'm going to spend time training it and wondering how well it works and perhaps looping between all three of these stages to get me better performance on my network, and then I'm going to deploy it. Given time constraints, I'm probably not going to talk about deploying it. So that's where we're going to spend most of our time. All right, let's start with what's my problem? My music genre classification problem. I definitely want to work out whether I can classify a short portion of some sort of audio into a set of known classes or genres. That's fundamentally what I want to do. And actually, if you go and look on the internet, you'll find quite a lot of exemplars of people doing this with deep learned networks. So I wanted to do something a little bit different. So I'm going to impose a bit of a constraint on myself. I don't really want to make too many assumptions about the type of network that I'm going to use, or the hyperparameters I'm going to use to train it, or possibly even the pre-processing that I'm going to use to do before I train my network. So I actually want to do machine learning around all of this stuff, and you'll see in a minute why that becomes interesting. However, having said I don't want to make too many assumptions, I'm probably going to have to do something. I'm going to have to make some assumptions because otherwise it's a bit unreasonable. So we're going to basically use image-like neural networks. I'm not going to specify exactly which one. I'm going to allow the network to vary, but we're going to use all of the research in the convolutional neural network space to help us classify these genres. And I happen to know that there is quite a lot of research that says converting sound into things like images works quite well to actually work out what the sound means and understand things about that. So I know this is fairly good. I'm also not going to use a recurrent neural network. I know, again, with signals that it might be worth thinking about how a signal varies in time and using recurrent neural networks to look at the properties, but I didn't want to do that. You could have done it, and it might be an obvious thing to try if my convolutional neural net doesn't work. And then I'm going to work on 5-second samples. I reckon it's not unreasonable that if you get your phone out and you Shazam for 5 seconds, everyone's pretty happy with that as the time bound. Okay. Given my requirements, everything starts with data. So whenever you do a deep learning problem, you need to have some data. And fortunately, on the internet is a data set called the GTZAN, or GTZAN, after George Tzikakis, who in 2002 recorded 1,000 tracks. There's 30 seconds of each of these 1,000 tracks, and he put them into 10 genres. Now, this was done in 2002. Fortunately, this means we will not be able to classify dubstep. I think that's a good thing. Some of you may not. So, I went to the internet, I downloaded this data, and I got a bunch of files. So the first thing I want to do, as with any good data science, is have a look at them. So throughout this talk, you'll see me stick up code. If at the end of the talk, you go and get my talk, and you bind my code together, you'll do everything. So I'm basically going to show you every single line of code I wrote over these 2 weeks as I learned to do this deep learning in Docker. So I use an audio data store. Data stores are things that let me look at lots of files on my disk. I read the first 5 and I plot them. There's my first 5 pieces of music. What I know from that is actually everything's 30 seconds long, as Jizan said it would be, but also there's not a lot of dropout. The data looks pretty good. Actually, I'm probably not going to have to do an awful lot of signal pre-processing before I think about how I do my actual processing. I went through a few more files and found that actually everything was fairly good. This is quite a good, clean data set. Okay, so having got my signals, how am I going to generate images? And remember I said I want to have a number of ways of pre-processing. So the first way that I'm going to do pre-processing is what are called MEL spectrograms. At the back, what is a MEL spectrogram? Well, you know what a spectrogram is? Awesome. Right. Does anyone know what MEL means in this context? Awesome. I'm going to teach you something. You all know there are 8 notes in an octave. Right. But when you think about octaves in frequency space, they double. The bottom one is 100 hertz, then you've got 200, then 400, then 800. So if you take the Fourier transform of a piece of music, you get an enormous amount of data up in the high frequencies, because there's lots of frequencies up there, whereas not a lot down in the low frequencies. But there's still only 8 notes up there. MEL means scale everything, so there's the same amount of data per octave of sound. This is a very good idea for anything that is actually audio in quality where you're thinking about notes. Unfortunately, MATLAB has a function called take me the MEL spectrogram with some window length and some overlap length and things like that. So I go and run this on 5 seconds of my data, and I get a picture that's like this of size about 256 by 212. That's quite a good size to do deep learning on. But I want to try other ways of doing pre-processing. So another way is something called wavelet scattering. Again, it's going to produce a picture that looks not dissimilar to a spectrogram, but it's a different way of analyzing the channels and the bands of music within it. Particularly, the bottom end of it is actually a set of spectrograms over places, but then this top chunk is like another set of filters applied to the output of this bottom chunk. There are ways of thinking about wavelet scattering that make it a little bit like a deep learned network, or at least a very, very shallow one. And it's actually well known that people can use wavelet scattering alongside traditional machine learning to do genre classification. So that's why I chose this as an alternative. Again, this produces an image of order 200 by 200. These are good sizes for doing deep learned training on networks. I've got these 1,000 tracks. We've decided on MEL and wavelet scattering, and I now need to convert all of my tracks from the GZAN dataset into spectrograms, because I'm going to want to train many, many models on them, so I don't want to do this transformation every time. So here's the code that does it, and that takes 5,600 seconds. I'm a parallel computing person. That annoys me. It should be able to be quicker. So all I want to do is say, how do I reduce that time? I go, a bunch of workers. I've got a bunch of processes. SPMD is a language construct in MATLAB that says everybody execute the code afterwards. I want to partition my data store into chunks based on how many labs there are across my workers. That says I've got 8 workers, I've got 8 chunks, they don't overlap. I run exactly the same piece of code, and that runs in 1,500 seconds because I ran it on my machine with 4 workers. And I could have run it on a parallel computer if I'd had more space and more resources. These are just quick techniques for speeding up how you do stuff. 3.5 times faster. Okay, so now we've downloaded our data set, we've converted it, it's a bunch of images in a bunch of files, we're ready to think about our network. And our network's gonna look a little bit like this. This is the standard convolutional neural network architecture. It's got some image inputs, it's got some number of this set of 4 layers, which is a convolution and a batch norm and a ReLU and a pool, followed by an exit layer, a dropout layer, fully connected and softmax. If you go and look at AlexNet or earlier ResNets or SqueezeNet or things like that, they all kind of look like this. But we're not going to use exactly that network. I said that I wanted to assume as little as possible about this network that we were going to put together. So I don't know what it should look like. I don't know how many blocks there should be. I don't know what the parameters of the blocks are. I don't know how much it pools. I don't know all sorts of things, and I can't a priori know them. So what should I do? Bayesian optimization. Who does Bayesian optimization? It's a mathematics institute. 1. Who knows what Bayesian optimization is? Ah, that's good. Awesome, thank you. So Bayesian optimization looks like a really, really great strategy for me. Let me tell you why. It sounds good because it's going to give me a global optimization of my problem. My problem is going to be which of my many trials of networks and pre-processing and blah, blah, blah works best, and it's going to globally give me the answer. It also operates on black box functions, and I'm pretty sure that the final quality of training a network based on a whole bunch of unknown parameters is definitely black box. If anyone can go and work out what the derivatives of that function are, I'd be impressed. And that's because Bayesian optimization doesn't require you to even compute or even think about what the derivatives of any function are at any given point. It doesn't work that way. So Bayesian optimization seems like a good thing to wrap around my training loop so that the network that I get out is wholly optimized. Right. So having decided that we're going to use Bayesian optimization, let's think a little bit about what parts of my network I'm going to optimize. So this is actually a sort of visualization of how a lot of convolutional neural nets work. Your image is some sort of size, let's say 256 by 212. The first set of convolutional layers that then batch norm, ReLU, and pool are a little bit like taking the spatial dimensions in your image and compressing them down into channel-like things and reducing the spatial content. Because you remember at the end of doing this convolutional neural net, you want to have a classification. You want to have an output that has a number between 1 and 10 or something like that. And so they often operate by pushing spatial dimensions into channel dimensions. So one of the ways they do that is by having a pooling size. That's the size that the convolutions operate over and then the size that they then amalgamate into one thing. We're going to definitely optimize over pooling and conv sizes. And the number of channels that they try and push the data into. So that's obviously, can you extract lots of data or not in any given point? The final pooling size is sometimes somewhat different because you're trying to get down into a softmax layer, which is where you then make your classification based on your outputs. And we're going to try letting the optimizer choose how many chunks of this 4-block thing there are. So are there 1 of them, 2 of them, 3 of them, 4 of them? In AlexNet, which was the first network that won ImageNet, they had about 4 of these. But more recently, you see somewhere to 6 to 7 of them as they try to classify more stuff. We'll also mess around with our dropout probability. We'll mess around with the initial learn rate and learn rate dropout. These are just hyperparameters of our training. In all, if we look at everything that I'm going to amalgamate and mess with, everything in a red box is something that I'm going to change at some point during this optimization. So quite a lot of my network is there. You've got no choice about images coming in and the initial batch normalization. That's just not interesting. So really, the only bit we're not doing is this bit of ReLU and batch norm and maybe the softmax. OK. Now that we've decided on how we're going to optimize everything and what we're going to optimize, we should make sure it works once, because I'm a software engineer and I know that I make mistakes. So fortunately, I built something a bit like this. I set up some training options. I gave it my image data store, and I said train. That there is the entirety of code to train this once. And I get an output, not unlike this. It says, my accuracy is getting better, my errors are getting better, and finally, in about 10 minutes, I have a training network. That's great. So how long is this all going to take? So if training one instance of one network is going to take 10 minutes, how long is the whole thing going to take? So Bayesian optimization has a rule of thumb, which is that for every variable that you have in your optimizer, you probably ought to run between 10 to 15, maybe 20 runs for that variable. This is like an absolute minimum. If you want to do better, you should do more. OK, so let's say we have to run this about 100 times. I've got 2 possible types of pre-processing. I've got 100 times. It takes about 1,500 seconds to run one. That is 3.5 days on my machine with my not unreasonable GPU. So who's willing to wait 3.5 days for their answer? This is great. I'm really pleased with you. Thank you. You would all say this, wouldn't you? Good. Fortunately, I have access to one of these things. This is a DGX station from NVIDIA. It's got 4 Tesla V100s and 20 cores and a lot of memory. Memory wasn't really a problem. But it's not my computer. It's somewhere else. So this is where Docker comes in. I've got MATLAB and the toolboxes installed on my computer, but I'm moving to a different computer. How do I do that? Well, clearly, I could just go and install MATLAB and the toolboxes, but actually, that takes time. Who's used Docker? Awesome. So with Docker, all I had to do was log in to nvcr.io, that's NVIDIA's GPU cloud repository. I needed to pull my 19A image, that's the one I released in March this year. I needed to rsync my data, and I needed to run MATLAB. And that runs MATLAB. It brings up, in a browser, a desktop that says, here's MATLAB. You double-click the MATLAB, and you get a little login. This is how the licensing happens. I log in with my MathWorks account details, and there, right in front of me, I have one of 4 Tesla V100s. At which point, I am now ready to go and do a whole bunch of compute on this machine. So let's put it all together. I go and get my image data store. I set up my 7 Bayesian optimization variables, and really all I have to give is the minimum and the maximum, what type they are, and perhaps what logarithmic transform I want or not. And then I make my Bayesian optimization run. This make cost function is a function that makes the network that we talked about from the Bayesian optimization parameters that it's given. And I also, because I'm a parallel computing guy, say I want to use parallel. This then says to Bayesian optimizer, would you please run lots of stuff at the same time and work out what the answers are? So then I sit back, I relax, I start getting answers. Each of these lines represents one 10-minute training run. And actually, over time, you can see that as the function evaluations, which is training of a different network, occurs, my cost function is reducing quite significantly. To begin with, it's pretty rubbish. It's not very good at working out what are good parameters for training these networks. But over time, it gets better and better and better. And you can even see right down at the end here at about operation 92, evaluation 92, it's found a slightly better global minima compared to where it was. Now, it was getting not significantly better down here, which is why I stopped it at 100. That was their sort of 10 times parameters. But you might run it and it might get better. So it comes up with a whole bunch of stuff, like particularly the number of the convolutional blocks. This says, oh, I want 5 of them, and I want pooling sizes of 3, and so on, and I've got my dropout rate. So particularly, it has chosen good parameters for this network. And it ran 117,000 seconds of wall clock time in 31,000 seconds. So that's a speed up of 3.76 on the 4 GPUs. This is pretty much GPU bound. That's where most of the time is spent. So I'm pretty happy with that. And the spectrogram, again, gave a 3.96 speed up, and again, gave a slightly worse result. So it'll transpire that the wavelet scattering gave slightly better parameters in terms of its pre-processing. What if that wasn't quick enough? What if even those two 30,000 seconds, which is of order 20 hours, was too slow? So up in Amazon, if I go into the EC2 cloud, there is an AMI called the NVIDIA Deep Learning AMI. And if I go and start that, and then I say I'd like a P3 16x large. So P3 16x larges have 8 Tesla V100s. I can go and rent that machine. It costs $15 an hour or $20 an hour, I can't remember, it's quite a lot. But it gets launched. As soon as I can SSH in, I do this, exactly the same 4 commands. And having done those same 4 commands, I get exactly the same thing again. And I run, and in that case, I end up with about a 7.7 times speed up on my things. Again, not quite 8, but close. So if you haven't got enough time, you could do the whole training run of both things in around about 9 hours on one of these machines. So the overall results, wavelet preprocessing was slightly better. We did get 3.1 days of compute down to 19 hours on the DGX or 9 hours on the P316X. And we know what our best network parameters are. So now we can go and train that particular set of network parameters and network, and now we've got our network that is the best one for music genre classification. And we obviously ask the question, is this any good? So again, we go and get our image data store, and we're going to test it out. We're going to take our validation set, not the set we trained it on, and we're going to classify our validation with our trained network and print the confusion chart. And actually, it's pretty good. Everything on the diagonal is where it got it right. And the thing that it was most confused by down here is whether rock and metal are significantly different. So those of you who listen to rock and metal, then sometimes they're not that different. Sometimes a little bit distressing that country is like pop, but there we go. All right, so this didn't seem to do too badly. I'm going to jump gears. Having finished with that problem, I want to now talk about detecting tumors in 3D brains. So this is a little bit like some of the things that the last speaker was talking about. There were MRI scans, and we have MRI scans in multiple channels across the brain. So this is data that's about 240 by 240, horizontal. You've got 155 slices, and you've actually got 4 channels. So unlike RGB, you've got 4 channels with MRI data, which are to do with other parameters that they measure. And what we want to do, well, what we're going to have is every single voxel in this chunk is going to be labeled tumor or not tumor. And what we want to do is train a network to recognize and tell us what each voxel is. So that's semantic segmentation using 3D type features. So to give you a picture of the data, here is a montage of all of our data, probably in one particular channel dimension. You can see we start with small things, it scans through the brain down to the base. Standard sort of thing you look at. But a more obvious way to look at it is this, with a volumetric distribution with rotation, so you can actually see where the tumor is. And we're not going to actually try to classify the whole brain. The way we're going to train this network is by taking small patches from the brain, 64 by 64 by 64, and train our network on those. And that way we can get more of these. All right. As with the genre classification, we have to do pre-processing. And I want to bring your attention to a couple things here. One of them is the use here of region 3 props. So when you've got a big picture of a brain in 3 dimensions, you've got a lot of extraneous space outside it. One of the things that's quite difficult is to put bounding boxes around things within the network, things within the image. Region props 3, is an easy function that simply goes and gives you the bounding boxes that then allows you to undertake channel pre-processing. So often you want to normalize the data once you've cut it down. This is a fairly standard mean standard deviation normalization. All I want to point out here is how easy it is to move this across to the GPU. Simply by adding move the data to the GPU, run the same code, and take it out, I've made all of this code in MATLAB run on the GPUs that are available. Now, that sort of normalization isn't sufficiently difficult that it's worth doing it, but something that we do later will be. So, there's the original, here's the final. You can see we've chunked out a bunch of stuff, and whilst you can't see it, we've also normalized. And we've saved that all to disk again. To get into our actual deep learning, we need to iterate over all of those volumes. That's what our image data store is going to do. And we need to go and get the data that labels every single pixel, because we've got another data store, because that's stored separately. The way that people label these things is not in the image. And then we need to join these two things together. And we do that with what's called a random patch extraction data store, because not only are we joining them together, we're also picking out these 64 by 64 by 64 patches randomly across the whole brain structure, and we're actually going to do it several times for any given volume during any given epoch of our data training. So having defined all of those, we then also want to add some sort of random augmentation at the end. So data augmentation is quite a common technique within deep learning to add more randomness. So particularly, what we're going to do is we're going to randomly sometimes rotate our cube of 64, left, right, up, down. We're going to flip it, we're going to rotate it, because we don't really know and we don't really expect any particular orientation on those cubes as we train our data. The other thing we're going to do is, having done those transformations, we're also going to move our data to the GPU and leave it there, because all of the training we're about to do is going to happen on the GPU. We're going to define our model, and this is a very standard semantic segmentation model. And the one thing I want to point out here is that all models in MATLAB also have a code representation. With a code representation, you can actually go and manipulate it in code and send people the code as well as the saved network. And as you're manipulating it, sometimes you make mistakes. So you might want to analyze your network and tell you what sort of errors there are. It's very common that as you build up these deep learned models, they have problems within them. And this then helps you understand where those problems are. So you train your model. This, you might see, takes about 4 days to train. So just training this one model rather than the 10 minutes for each of my genre recognitions. So obviously, I've got a bigger machine. I've got that thing, and I quickly run a little version of this model, and I say, right, where's the time spent? And the time is spent in computing the gradients of the network and in actually extracting data from the data store. And there are 2 easy ways to make these 2 things faster. When we had our training model parameters, all we needed to do was say, instead of dispatching our data in the background from false, we can say do it, go and load it somewhere else and give it to me as soon as it's available. And I want you to use multiple GPUs if they're available. Doing those two things, I go from a serial time of 1 all the way for background dispatch adds about 1.2 times speed up. 4 GPUs goes just less than 4, and together gives me about 4.4 times speed up. That's a really good thing, especially it goes to 8 point something up in the cloud. So having trained my model, we again ask, is it any good? This is the code that goes and says, use semantic segmentation on whatever network we generated on my validation data and filter it in 3D. That's a very common thing to do with semantic segmentation. And again, do it in parallel. So this time, I'm using a parallel for loop, and again, partitioning the data and concatenating the results. That speeds this up by about 4 times on 4 cores, and many times on many cores. And then visualizing the results, the original is on the left, and the final is on the right. Some of them, it's pretty reasonable. There are places where it doesn't quite get it right. This might indicate that there are different networks that you might want to bring in, or possibly that there's more data. This was actually trained on only about 170 patients, and you would like quite a lot more data to get a better network out of this. And with that, I think I'll pass over this bit, which was all to do with deployment, and say, in summary, I think I've shown you a simple way, and with a simple way to undertake data preprocessing with extensive analysis functions. There's a flexible training environment you can play around with. It generates all the right networks, and you can qualify them. And as with many places, MathWorks, thank you for saying this, Mark, is based here in the UK. We currently have 13 positions in the development organization, and I know that another 15 to 20 are going to open in about the next month. We're always hiring. Please talk to us. Thank you very much.
Thank you, John. Any questions?
It's a great talk. Very nice. In the first example, genre classification, did you say that you just got 1,000?
I only had 1,000 songs. I only had 1,000 training entries. I'd love to have more. It's rubbish. Yeah, I totally agree.
Right, because I mean the number of parameters in the model that you're training would be about.
It was quite a small model, so in the end, it didn't end up being. It was about 50 megabytes in size. Remember, it's not 1,000 entries. You've got 1,000 times whatever sample size I had. Yes, I just worried about the size of the network that you're presumably trying to train for that, and then the Bayesian optimization. I totally agree. I would love it. If someone can point me to a bigger data set of genres, I would absolutely love to do it. I'm fairly confident that this strategy will work. It'll just take longer. One of the problems with deep learning today is there just isn't enough data out there actually to get that is valid, that is reasonable, that's got enough stuff. So data is the thing that is going to be the commodity in the future, actually.
So have you tried your model on standard benchmarks like ImageNet, etc.? Because we have known accuracy, whatever.
I think exactly what I did, you could absolutely try on ImageNet and see what happened. ImageNet's really big, so I think what you'd want to do is you'd want to cut ImageNet down to some reasonable subsample, do the optimization on that, and then train the final thing on a significantly bigger full ImageNet stuff. Unfortunately for us, ImageNet has certain legal issues that are not well known. Great. Okay.
Good. Thank you very much.
Thank you very much.
That was